Okay, let's get started. Thank you. Welcome to the HAO Colloquium. And today we're happy to have Dr. Joe Huba from NRL as our speaker. And here are some data points along Joe's career path. And it's a bit long, so bear with me. A lot of data points. So after receiving his PhD in physics from the University of Maryland, he went to NRL, at first as a postdoc, and then stayed on as a research physicist. And while on staff at NRL, he also got a MBA degree from the University of Maryland, which is not something I always see on a physicist resume. But and his research interests include plasma boundary layer, ionosphere and magnetosphere processes, wave and instabilities in plasma environment, 3D Hall reconnection processes, and modeling of the Earth ionosphere and plasmasphere, which is given talk about today. And he's a fellow of the APS, American Physical Society, and also AGU fellow. And among the many awards, just want to mention that he got the very prestigious NRL E.O. Hubbard Award. And then last year, he got the Dr. Dolores M. Atter Top Scientist and Engineer Award from the Department of Navy. And recently, he's appointed to the HAO affiliate scientist position, which I'm sure Joe considered to be his most significant achievement so far.
Thank you, Manley. Thank you.
And
Okay.
you're welcome to ask questions, and this is webcasted. Remember that.
Okay, thanks again. So I'll talk today about our recent work modeling the plasmasphere with SAMI3, and my colleague John Kroll's also done a lot of this work as a team. So we started the ionosphere, and this is actually to scale pretty much. The sun is off to the left. We have dawn, noon, sunset. And you can see the ionosphere building during today, intensifying in the afternoon and dying at night. And it's a relatively thin layer, a few hundred kilometers thick around the Earth. We all know it's primarily caused by the sun's radiation, hence it's bright in the daytime. Typically 90 to a few thousand kilometers for nominal parameters for the ionosphere. Maximum densities are a few times 10 to the minus 6, but at a few hundred kilometers, it's still dominated by neutrals, so it's a very weakly ionized gas in the sensible ionosphere. Multi-ion, molecular ions below 200 kilometers, atomic ions above 200 roughly. Extremely low beta plasma, 10 to the minus 4, 10 to the minus 5. So the magnetic field is like an anchor. It just simply doesn't move around like you see in MHD processes like in the magnetosphere. I say cold, I don't know, maybe it's not the right word, but it's usually a few thousand K or less in the ionosphere. Anisotropic conductivities, and because of this, we usually assume that the magnetic field lines are equipotentials. Okay. And this is Grabowski's relatively famous cartoon, and it shows a lot of things going on. And loosely speaking, this is the plasmasphere extending a little bit above the Earth along closed field lines. So this is a picture from the image satellite showing the plasmasphere looking down from over the North Pole. The sun is to the right, and this is emissions from helium ions. And some of the key features, at least morphologically, is there's typically a tail in the post noon sector, the afternoon sector. There's also a shoulder. And as people have looked at these images, there's some other fine scale structures going on. So it's kind of like identifying different characteristics on some animal of some sort, giving them different names. But the tail is the most prominent. The density, say high density here, so in the plasmasphere, you are looking at densities greater than about 10 to the 2. At the edge of the plasmasphere, you get a very sharp fall off and the densities drop by an order of magnitude or more. It's mostly hydrogen. There's helium and some oxygen during disturbed times. A range may be roughly L equals 2 to 7, depending on geomagnetic conditions. And then the dynamics during storms, you can have this situation here, and I'll show in the next view graph, the plasmasphere reconfigure relatively rapidly, i.e. hours. After it's reconfigured, then it goes back to its normal state, the relaxed state, and that can take many days to refill. So this is an example of before and after a geomagnetic storm. In this case, it's relatively diffuse and relatively large compared to here, where it's contracted quite a bit, and you get this extended plume coming out around the sunset sector, post-afternoon sector, which is relatively common. So I showed the picture that Joe Grabowski had put out, and this structure was actually explained by Grabowski back in 1970, and this is just a cartoon based on our work. And so looking down from the North Pole, the sun is to the right, and these circular lines are the co-rotation potential. So this would be the plasmasphere trapped on closed field lines. These potential field lines are the convection field associated with the solar wind magnetosphere interaction. So we have plasma coming in from the left and then going out to the right. During a storm, this convection potential intensifies as shown here, and plasma that was circular going around here can now come up here and then exit to form this tail. So this is just sort of a cartoon description of how this tail can form based on the reconfiguration of the potential structure in the magnetosphere during a storm. Here are some data from the plasmasphere. It's from Baruba. So L equals 2 out to 5 in the roughly equatorial plane. And so enclosed, we're at 10 to the 3, 10 to the 4, and then at L equal 5, 10 to the 1 to 10 to the 2. And this is a fit to that set of data. One thing when I was going to talk, it was an interesting question from Sunnerup. You know, it's pretty diffuse down here in terms of a scatter of points, but this is actually relatively sharp, which is pretty interesting and something I'll talk about later. This is some more data. What this data shows is how the electron density varies along a magnetic field line. So if you're here and as you start moving this way, you would be moving this way. So as you go down closer to the Earth along a field line, the density is increasing. Okay, so that's sort of like a generic overview of some plasmaspheric properties, the density and how it deforms during storm time. So now I'll get into our model and how we try to capture some of these features. So this is a description of some of the key points of the model, but I highlighted two things. One is in red, we have hydrogen and helium. So since these measurements by image are helium ions, it's significant to actually have helium in the model as a way of diagnosing and comparing to data, even though it is a small component, 5%, maybe 10%. The other thing in this particular set of simulations is we've modeled the high latitude convection potential using an analytic Volin-Stern model and also using a Weimer potential model. I'll skip it, okay. So these are the fundamental equations we're solving. Ion continuity and ion velocity for 7 ion species, and ion temperature for 3 species, hydrogen, helium, and oxygen. And there's also two electron equations. One is ambipolar equation for the electron temperature balancing the parallel electric field, and there's an electron temperature equation. And then for the neutral wind dynamo, we include a potential equation to solve for the low to mid-latitude dynamo electric field. So in this particular model, we have the neutral wind dynamo field, and then we have a co-rotation field. So another great simplification in this particular model is we have a magnetic dipole axis aligned with the Earth's spin axis. And then for the first set of studies, we use a modified Bohlen-Stern-Maynard-Chen potential with a time dependence. And so we run at, we'll say, relatively low potential, ramp it up for 8 hours, hold it steady, ramp it back up, hold it steady, bring it back down, and then hold it steady for a number of days. So I'll show results during this phase of the evolution of the plasma going through two little storms, and then talk about refilling. Just some numbers. For this particular set of simulations, the maximum magnetic latitude in the model is 78 degrees. Relatively mild conditions, F10 170, day 80, and these are the grip parameters. Outside of L equal 8, we added a loss term. So we just sort of drain plasma away, trying to replicate open field lines, plasma just leaving the system. This is something that needs to be worked on, but for the time being, it doesn't seem to affect the results, and it keeps things relatively quiet, far away from the Earth. So, and the top figure is after running a few days with a relatively low potential. On the left is hydrogen, on the right is helium. These are color contours looking down from the North Pole, and they're on the same scale. This is 1 per cc, and then the red is 10 to the 4th. And so I'll show some plots later, but basically you can see there's a lot less helium than hydrogen, trying to compare colors at the same distance, 5 or 10%. And so we see at the end of quiet times, we have a relatively nice toroidal type plasma. This is after we increase the potential significantly. Can't see it, I don't think, but there are potential field lines on here, and there are a lot more here. And so this relatively large structure has now contracted, similar to what we saw in the image data. And then we see this tail forming and coming out after in the noontime sector. Michael.
Magnetic field model, do you have any compression on the day set, or is it just a pure dipole?
Pure dipole. So this is extending to the regions where the model shouldn't be extended to, but yeah. This is hydrogen, and then this is helium, and the same type of behavior seen in both cases, although you know, the so-called tail or the extension out in this region isn't as dramatic in the helium as it is for the hydrogen here. And I think maybe a movie may show. That's the first storm and then the second. So I'll allude to this later, but you can see the, well, yeah, you can see the potential field lines are jiggling a little tiny bit. And that's because of the neutral wind dynamo. If you turn that whole feature off and just have the Bohlen-Stern and co-rotation potential, of course the potential lines don't change other than we change them empirically, but they're very symmetric in the north-south direction or up-down direction here. So that was the hydrogen, and then the helium, again, is similar. where it comes down, and you can see some extension out in this direction, but it's not terribly dramatic, but it is there. Okay, another view of this is now looking north-south, and the sun again is to the right. And this is at the end of the quiet time run. And this whole section in here is sort of the plasmasphere. I think we do a pretty good job on modeling. And then this is after the storm goes on, and this whole section here is now contracted in substantially. There's some contraction here also, but not quite as dramatic as the nighttime here. And then some of these features out here are field lines that go beyond L=8, so that's where we've modified the plasma. It's partially responsible for some of these wings that come out. This quasi resembles one of these stealth bombers, I think, right, with the jaggedness here. Okay, and the last image, this is now, again, the same information, just shown as a 3D iso contour surface, hydrogen, helium, hydrogen, helium. And so here you can see in both cases, it's relatively nice toroidal plasma. And then after the storm, when we've increased the potential, you can see this tongue, or not tongue, or tail coming out at this section here and a little bit here. There's a feature here which not sure what to make of, whether it's graphics or there's something funny, but nonetheless, it's pretty toroidal in general. So these are actual plots of the density as a function of L shell for hydrogen, for helium. The solid lines are the quiet time values, and these dashed lines are the storm time values, or after the storm. And it's most dramatic in the midnight sector, where we can see that the plasma pause has come in dramatically. There wasn't really much of a plasma pause in the diffuse case, but right around here there's a big change in the density, where it drops off a few orders of magnitude over a fraction of an RE. General, they've seen some plasma boundary layer is very, very narrow, much narrower than here. So some of this is just simply the gridding in terms of capturing a much finer scale. But in the dawn sector, you can also see it reasonably well here. Not so much in terms of the noon and dusk sector, although there is a break around that point. And you get also the feeling, or you can see, relatively speaking, out in the plasmasphere, the relative magnitude of the helium to the hydrogen ions is about 10%. And they track each other reasonably well once you get out past L=2. Okay, so this is some data I had shown earlier. And so we took our results and plotted it here. And so it looks pretty good. The slope is decent. We're a little bit low on density. So wasn't quite sure why this was. And looking over the code, the story goes, when we first developed SAMI 10 years ago, we have a photoelectron heating model that was Bailey's model. That's relatively simplistic, but it kind of works. And we compare it to Millstone Hill data, and comparing the densities and temperatures, things look good. All right. Go forward about 6 years, and working with Heisel, we're trying to compare our model to Hickamarka data. And the densities look decent, but the temperatures were too hot. So we went into our photoelectron heating model and just put a factor of 0.15 in to bring down the temperature. Then the temperatures now agree with Hickamarka. Okay, so the temporary 0.15 factor turns out wasn't temporary. It sort of morphed its way through our various versions of the code. And so when you take it out, then you get this sort of reddish type thing. And so it shows that, you know, the electron temperature is pretty important in trying to figure out or understand the dynamics of the, you know, the scaling in the plasma densities. Yes, Dolores?
Is that a globally averaged, or is that on some longitude?
Our results are globally averaged in longitude. The data, I don't know. I think it's primarily on the nighttime, but that needs to be, I have to look a little bit more into that.
Okay, well, the agreement now is really very nice.
Yes, well, yeah.
Okay?
So then I thought, well, I'll just crank up the electron temperature, and maybe I can get something up here, and then maybe that would indicate there might be some temperature that the ionosphere can't get hotter than, or at least during these periods. And I'll come back to this at the end of the talk. Yeah, this is that empirical fit to the data, slightly different than the last one, but for quiet times. And then these four curves are our equatorial densities going in noon, dawn, dusk, and midnight sectors. So again, in this region here, the slopes are pretty good compared to the data. And again, we're a little bit low because this is based on the older, colder ionosphere. And this was, again, you know, comparing to this data along a field line. There's not much variation from the data because it doesn't go to low enough magnetic latitudes or high enough, however you want to look at it. But these data points that I X'd in here with the symbols are data, and then these solid curves are from our model, SAMI. So again, you get some variation down here, but when you go to the higher latitudes, closer to the Earth, then the density takes off, and we're a little bit low, again, on the density. But this is just one realization, one simulation. Okay. In the next study, this is mostly done by John Kroll. We have a state here where we're at the end of our second storm, and then you relax the potential, and you can see, you know, how much it's relaxed. And then the idea is you start to fill up this region out here, and how long does that take? And that's the refilling process. And the answer is many days. So this is after one day. You can see some rattiness and everything here, and then the next day this section is, you know, filled up, and it continues to fill a little bit as time goes on. And the same thing here. 1 day, 2 day, 3 day, you begin filling it. So this is a lot of lines. L equal 3. The dashed line here is the average refilling from our model at L equal 3. The colored lines are the refilling at dawn, dusk, midnight, and noon. So in terms of a longitudinal dependence, there is quite a bit at L equal 3. And then if you average it all out, well, you get, you know, one line here. And then this dashed line is an empirical data model from Richard Denton that he put out a few years ago. So early on, in this particular case, it agrees reasonably well. This is L equal 4 and 5. Maybe very early on in the first day, our slopes agree, but then we turn over and start slowing down as we refill the plasma. So this is hydrogen, and then this is helium. You get the same general features, except there seems to be more variation longitudinally in the helium than the hydrogen.
What causes those diurnal variations? Oh, sorry. What causes those diurnal variations in both cases?
I think we have the neutral wind dynamo in there, and that affects it on a daily basis and modifies the potential. So that's the primary thing. That's something we're looking at right now in more detail. This is John's most recent study. So instead of using an analytical model, in the first study we allowed control over, we actually used solar wind data to drive the Weimer model. And this is the solar wind conditions. There was a relatively small storm. Then afterwards there's this quiet period here. And so we modeled this entire period focused on the quiet time for the refilling. On the right is some refilling rates. The NDT as a function of L from Richard Denton. And the symbols, the black circles, are actual data. And then there's a solid line through here, which there is a fit to the data. And I don't know what D sub n is. Well, anyway, Richard did it. I don't know what that is, but the important thing is the solid line and the fit he has to that. So this is similar to the last figure, except it's electron density, both hydrogen and helium. And again, this is our refilling from the model at L equal 4, 4.8, and 5.4. It's not as dramatic as the last case, because the last case was an idealized storm, which we really hit the system hard. This was kind of a small storm, but you can still see it's refilling and starting to turn over. And then the dashed lines are this formula, which was given by Denton in his empirical fit model to the data. So overall, the slopes here are reasonably good, especially here at the beginning, early on in the refilling process. I alluded to this before. This case on the right is the potential and the shape of the plasmasphere without this neutral wind dynamo turned on. So you just have a co-rotation field, and then superimposed is the Volin-Stern model. So about this axis, it's symmetric as far as the potential is concerned. And in the right, we had the wind dynamo turned on, and now you see it introduces something of an asymmetry. And out here, it's not quite so circular. So there is an effect we're seeing from the neutral wind dynamo on the plasmasphere. Okay, so I said in this particular model we have a co-rotation field, so the Earth's axis is aligned with the spin axis of the Earth. And so for numerical reasons we can set up a grid, and it's fixed relative to the sun, and the Earth is sort of like spinning underneath in essence. If you now were to tilt that, then this whole grid would be spinning and would make things really miserable. So the alternative is, as the original SAMI we wrote, we didn't have a co-rotation potential. The sun goes around the Earth. So that's a comparison of what I've been showing you, where we have a co-rotation potential, and then in this case we turned off the co-rotation potential and now just have the sun spinning around the Earth. And so it's hard to see because the potential field lines aren't very visible, but there are circular field lines here, which is the co-rotation potential dominating, and then over here you can see potential lines coming out, not circular. And so this is before the storm, and then this is after. And in a broad sense, you know, the two figures agree reasonably well. So i.e., whether we have a co-rotating potential added or not, the results are reasonably similar, which actually is a pretty good thing. If we convince ourselves that this is good, then we can tilt the dipole and then investigate the plasmasphere behavior for more general conditions. This is a plot comparing densities out of the magnetic equator for the two models. The black lines are for the co-rotation case, and the red lines are for the no co-rotation case. Okay, so in a broad sense, they look pretty good. There are variations, some here, some out here, small variations. We need to do more work. But some of this might be actually gridding, you know, or lack of sufficient gridding. But again, I think it's a little bit comforting that both cases give roughly the same results. And if they didn't give the same results, well, one, I wouldn't show it, and two, I wouldn't know what to say about it. Okay, so this is kind of new in looking at temperature. So earlier I said, you know, there's a sharp upper boundary from the data, and I thought if I just crank up temperatures, I might hit that upper boundary, and that would be interesting. But we never really looked at temperatures a whole lot in the code. We've been fixated on densities and comparing to observations the best we can, which were density. So here, this is before the storm. This is the plasmaspheric density, and these are temperatures. And it's a little bit different. I've changed scales here. Instead of going from 0 to 4, I'm going 1 to 5. And so the densities are roughly the same. Well, they are the same as before. But over here in the ion temperature, inside the plasmasphere, it's relatively cool. But we have this ring of hot plasma extending just outside the plasmasphere. And then this is after the storm. Again, this region has shrunk in quite a bit, but you still have this ring of hot plasma sitting on the outside. And it's a little bit, well, let me say worse. So one of the problems in dealing with this is when we developed the model, we put a upper limit on temperatures of 10 to the 4 K. And so in these regions here, we hit that limit. Okay, so this is the max the code was allowing it. And so if we relax it, it can even get hotter. And then this is the same data except at a different viewpoint, north-south. This is noon, or rather midnight. This is noon. Again, there's hot torus of plasma sitting out here. And as the storm goes on, it's actually cooled off quite a bit, but nonetheless, trapped inside here on the outside is this hot plasma. So this just became apparent actually a couple of weeks ago to us. And so the first thing is, well, is there any data that would help you support this? Well, I'm one step ahead. And I said, okay, so what is happening? Why would this even get hot? Well, in our temperature equation for the ions, there are terms proportional to the ion velocity along the field and its gradient. And in these particular hot flux tubes, the ion velocity is getting rather large, many tens of kilometers a second. And so it seems, these are the two terms that are responsible for the heating, and we have to go back and actually go through some studies to figure out which one's dominating why, and is it real or is it something wrong with the code. So at least there's a reason or somewhere we can point to in the code that would exhibit the temperature getting hot. Okay, now back to data. Yeah.
trying to understand that equation. Would that include the effect of, as the flow is out, the flux tube's getting wider, so you're tending to get adiabatic cooling of the
Right,
plasma?
yeah.
Is that included in this? Is that
Yes.
that's the 2/3 TI?
Well, I left off all the geometric factors in the magnetic field, but the answer is yes, that geomagnetic factor's in there. That's why this needs work. Okay, so we have done studies in the sensible ionosphere. And Helix have reported data where if you have strong meridional winds pushing plasma from one hemisphere to the other, as the plasma is coming down on the other side, you can get ion heating. And it's from this effect of adiabatic heating. And so when we did some simulations, we captured that heating and that effect. And we've also done some other spread F studies showing this adiabatic type effect. So that part's good. It's expending it out into this netherworld far out from Earth. We have to figure out what's going on and why. But yeah. I forget the second author, and I think the first one was Sorbouet. 1970 JGR OGO 5 data. They had a number of curves showing that the ions get hot going outside the plasma pause. And in their data, 10,000 to 50,000 K. So that's kind of good news, which suggests maybe our results aren't total nonsense. I haven't gone through all the details here, but there was a lot of work in the 90s by Jim Horowitz and colleagues investigating these types of behaviors with semi-kinetic and hydro fluid models. And I don't have the exact reference, but I believe it was Wilson in 95 actually used a hybrid code where he used kinetic ions, particle ions, embedded in electron fluid to do simulations of dynamics along a flux tube at relatively high altitude. And in their kinetic studies, they were getting ion velocities of tens of kilometers a second, and they were also getting heating of a few 10,000 K, at least under different conditions. So from data and from some other numerical studies, there's a hope that the code isn't completely bogus, although we're pushing it in regimes where it's a little bit nebulous, but some of these issues have to be addressed as to why it's heating. Whether it's numerical or not, I don't know, but there's a hint that it could be real, that we're capturing it within the code. So that's pretty much it. So we've been, okay, I was going to say, we've been doing this for maybe the last year or so, but we actually have been doing it longer. It's been 2 years. The first year, we were getting results, and the code ran, the results were awful, and during one of the editings of the code, one line was commented out that shouldn't have been commented out, which said the magnetic field drops off like 1 over the R cubed or whatever. So if the magnetic field is constant with space, you get different results. Anyway, after this bug was corrected, this is pretty much the way the code has been running. So in a broad sense, I think the simulations agree with image. Overall, we're not getting a really sharp tail like they see, or plumes for big storms, but that's largely, I think, not having the right high latitude convection potential in the code right now. The density profiles, hydrogen and helium ions, compare fairly well. Helium to hydrogens are usually a few percent, 5 to 10%. And I indicated we get pretty much the same results, whether it's a co-rotation potential or not. What are we doing now? Well, we are using the Weimer potential for a lot of studies. That's going on. I told you we have a loss term at L equal 8. It would be better if we actually knew where the open closed field lines were so we could improve that fix to the code. There's a lot of diagnostics that actually need to be done. The image data is just sort of line of sight H plus emissions, and what I was showing was just simply real density values. And so then we have to start doing the line of sight integrations through the code so we can compare with the image data. And we have some programs working with Pontus Brandt at APL, and that should be done, I hope, in the next few months. Then the other big thing is, it's one of these things, we're going to do the Plasmasphere, so here's the Plasmasphere. Well, we also have an ionosphere in there, so we just have to start looking into how the ionosphere respond. Well, we have the data, we just haven't looked at it, but do more studies on how the ionosphere responds to storm times and this plume evolution and the stuff John Forster has talked about. Aside from using Weimer and analytical models, it would be nice to get potentials from LFM and or RCM, especially during storm times, to drive some interesting features. And this is new. Again, this just came out in the last couple of weeks. This whole ion electron temperature thing needs to be understood a lot better. Make sure we're doing it right, and if we're not, to try to fix it. But as things stand right now, things look reasonably good with our model actually reproducing the generic behavior of the Plasmasphere. And so this is where we're going. Thank you. Michael.
So in your plot that showed the longitudinal refilling rates and the variation thereof, I think it was the helium plot, it had the noon and midnight refilling rates looking pretty much the same, and then the dawn and the dusk having variation over there. And I was just intrigued why noon and midnight would have such a similar refilling rate, given the underlying ionospheric density variations. That one. So yeah.
Okay, so one answer is no. I don't know right here. This is stuff we're doing with crawl right now, trying to unravel all these variations. They're pretty much tied into the fact that we have the neutral wind dynamo turned on. This goes away if that's not there, at least these variations. So I have to pinpoint in detail what's happening. Yeah, that's
I'm kind of going from memory, and I'm not sure this is right, but I recall having seen observations comparing magnetic pulsation data that give sort of the mass density along field lines with electron density measurements from, I'm not sure if it's Whistler's or what. So getting the ratio, estimating the mean molecular weight of the ions out around the equator. And I vaguely recall getting, they were finding numbers around 2 or something, which would indicate a helium to hydrogen ratio quite a bit greater than 10%, be more like 30 or 40%. Is there any way to get the model to produce much larger helium fractions?
I haven't quite seen that. I know when people were looking at that during storm times, they think a lot of the variation is because there's a lot of oxygen out there. So there's been a lot of concern during storm times, oxygen getting out, and that's having the effect I think you're suggesting they see, not just helium. As far as helium getting out to be 30 or 40%, I don't think I've ever heard that mentioned, actually. Occasionally in the regular ionosphere, there's been suggestions that occasionally helium can dominate over, say, hydrogen or oxygen occasionally, but not to the extent you're saying in the plasmasphere, as far as I know.
Maybe this is kind of naive question. When you see the temperature, show the temperature before and during storms, why it's cool down during the storm?
That's what we have to look into. Like I say, it's tied in, I think, to plasma velocities and the like, and has to figure out which term is doing what and why, the plasma velocities are just maybe getting very small for, as the dynamics goes on. Yeah, this is, okay. I made these plots Monday, so, yeah, so I'm just letting you know, this is, it's sort of interesting, intriguing, and maybe problematic for us, but this is something I think is relatively important.
What's the highest energy oxygen or helium that you've ever seen in your model?
Gosh, that's a terrible question. Okay.
Observation.
Well, you don't want to believe my model when you ask that, but okay, so we put a limit of 10 to the 4th K. I did at least one run where I changed it to 10 to the 5th K, and there were some regions that would get that hot. And so I'm tempted to think it's not real, but again, that's why it has to be looked at. The reason I don't think it's real, well, because it was saturating, and it wasn't quite as, how should I say it? The bottom line was there were regions in space where it hit that limit of 10 to the 5th. So if I made it 10 to the 6th, maybe I would have gone that high. So, but I think it might be regions out in space where the gridding's bad, other things could be going wrong. So, it just needs to be figured out.
And I have a question. So for the neutral wind, is it resolved by the model, or is it from for the neutral? You said the neutral wind dynamo plays a role in in this process, and
Right.
plots they're different.
Yeah, so John Kroll's doing this study now. I don't have any results, but so we've run it for HWM93 and HWM07. Because you have different wind models, you get different dynamos, and some of the behavior of the plasmasphere is then different, where the bumps are and things like that change. And then we'll try some time GCM data and see how that, basically what we're showing is you change the when, you change the answer type thing. And so so what we want to do is to see and understand how much and how the neutral wind dynamo is actually affecting the plasmasphere.
And is the most important contribution from F region or most sensitive to E region? Do you know?
No. Still working on it. That's all I can say. It's
Yeah.
it's the standard. You do a run to solve one problem, and then 3 more pop up, and so it proliferates. This is sort of a progress report.
And maybe a very ignorant question. You said that L8, you set, basically it's you
Yeah,
just
put a
let-
big loss term in, but yeah.
And I would think that in a solar event, that could be a first place that, got hit, and you can have input from
Yeah.
those region. So will this be a very realistic assumption during a, strong event?
Well, realistic, no. The flip side is if, like talking about Mike, if we can get the LFM potential and everything working, we could also get some density data out at that region. So we could feed in, say, the LFM densities at that region rather than have some, loss term that I put in to keep things sensible. Yeah. Yeah, so, yeah.
Questions for Joe? Oh, not more. Let's thank Joe again.
Good.